Welcome to GATE class. So today we will see the Fourier analysis of discrete time signal and system. So today we will start the Fourier analysis of discrete time signals and systems. The Fourier analysis plays the same fundamental role in discrete time as in case of continuous time. So as we will see when we will proceed, that there are many similarities between the techniques of discrete time Fourier analysis and their continuous time counterparts. But also there are some important differences. So let us start with discrete Fourier series. Let us start with discrete Fourier series. So what is the discrete Fourier series? So let us start with the periodic sequence. So a signal xn is said to be periodic when we have n plus capital N. If what is capital N? Capital N is a positive integer, so that x n plus capital N is equals to xn for all values of n. Then what is capital N? So capital N is a positive integer. Capital N is a positive integer. Also we have complex exponential signal. So suppose if we have xn, that is equals to e raised to the power j 2 pi divided by n naught into n, then it can be also written as e raised to the power j ohm naught into n. So what is that? Ohm naught. So ohm naught is equals to 2 pi divided by n naught. That is basically the frequency. So if it is periodic, so as if we are saying that this is periodic, then e raised to the power j ohm naught plus 2 pi k into n, it should be equals to e raised to the power j ohm naught and e raised to the power j 2 pi k n, and that is equals to e raised to the power j ohm naught n. So it is basically, if it is periodic, then this basically this is periodic basically because this is k integer, some k is some integer value, so it is integer multiplier. So basically 2 pi k is basically when we have k is equals to 1, then it is 2 pi, k is equals to 4 pi. So if we are adding this, then we are getting the same thing because it is periodic. Okay, so let us denote psi kn. Let us denote psi kn is equals to e raised to the power j k ohm naught into n. And what is ohm naught? Ohm naught is equals to 2 pi divided by n naught. And what is k? K is equals to 0, plus minus 1, plus minus 2, and so on. So this psi 0n is equals to, is denoted is in this manner: and psi 1 n is n naught plus 1. So basically we are using this periodicity property, and just like we have psi k n, and that is equal to psi n naught plus k in bracket n. So just we have used the periodicity property. So in short, if we have psi k n, that is equal to psi k plus m n naught n, and what is m? M is an integer. M is an integer. So let us see the discrete Fourier series representation. Discrete Fourier series representation. Let us see the discrete Fourier series representation. So the discrete Fourier series representation of a periodic signal, the discrete Fourier series representation of a periodic sequence xn, of a periodic sequence xn with fundamental period n naught, with fundamental period n naught is given by xn is equals to summation k is equals to 0 to capital N naught minus 1 ck e raised to the power jk ohm naught n. And what is ohm naught? Ohm naught is equals to 2 pi divided by n naught, and n naught is the fundamental time period. So what is ck? So ck, where ck are the Fourier coefficients, where ck are the Fourier coefficients, and it is given as ck is equals to 1 divided by n naught summation n is equals to 0 to capital N naught minus 1 xn e raised to the power minus jk ohm naught into n. So what is that xn? So if this xn can be represented in this manner, the xn can be represented in this manner: summation k is equals to n naught ck e raised to the power jk ohm 0 into n, and that is ohm 0 is equals to 2 pi divided by n naught. So ck is also we can write in this manner: 1 divided by n naught summation xn e raised to the power minus jk ohm naught into n. So where summation k n naught denotes that summation is on k. And what is k? So k varies over a range of n naught. K varies over a range of n naught. Now setting k is equals to 0. Setting k is equals to 0. What we will get? We will get C naught, that is equals to 1 divided by n naught summation n is equals to n naught into x n, that is C naught. So which indicates that this expression indicates that this C naught expression indicates that the above expression, the above expression of C naught indicates that the above expression of C naught indicates that the average value indicates the, basically it indicates the average value, it indicates the average value over a period, it indicates the average value over a period. So next important point is convergence of discrete Fourier series. We have seen that in case of continuous Fourier series also there are some convergence points that is given by Dirichlet. So here we have also, we can see is there any convergence issue for discrete Fourier series or not. So since it is very interesting, since the discrete Fourier series is a finite series, in contrast to continuous time case, there are no convergence issue with discrete Fourier series. There are no convergence issue with discrete Fourier series. Now let us see the what are the various properties of this. So let us see the various properties of discrete Fourier series. Properties of discrete Fourier series. So first property is periodicity of Fourier coefficients. Very first property is periodicity of Fourier coefficients. So basically if we have this relation for periodicity, the Fourier coefficients are basically following this condition that Ck plus n dot, if we add that n dot with k, that is equals to Ck. that is equal to Ck. So what it indicates, so which indicates that Fourier series coefficients Ck are periodic with fundamental period n naught. Second property is duality. So what is that duality property? So if we have a Fourier series, that Fourier coefficient, let us denote it as Ck. Basically Ck or Ck both are same thing. So Ck, that is equals to summation n is equals to over the range. Basically this summation over the range of n naught 1 divided by n naught xn e raised to the power j minus jk ohm naught n. This is the standard formula. Now if we let n is equals to minus m, what we will get? We will get Ck is equals to, now we are going to take summation over the range of m, and it is equals to 1 divided by n naught x of minus m, because we have taken n is equals to minus m e raised to the power jk ohm naught into m. Now what we are getting here, if we letting k is equals to n and m is equals to k, in this expression, what we will get? We get C of n is equals to summation. Now summation is over, if that variable is k, it is over the range of n naught 1 divided by n naught x minus k e raised to the power jk ohm naught n. Now if we compare this, suppose this is equation number, if we compare this equation with the standard Fourier series coefficient expression, what we will get? We will get that 1 divided by n naught x of minus k are the Fourier coefficients of Cn, So if we adopt the notation, Xn, that is discrete Fourier series of Ck, that is Ck, then to denote the Fourier series pair, Cn If we find out the discrete Fourier series, then it is equals to 1 divided by n naught x of minus k. It is very simple. So this property is called the duality property. This property is called the duality property. So this xn has discrete Fourier series ck. Now if we replace k with n, and if we find out the discrete Fourier series, then it is 1 divided by n naught x of minus k. Instead of here n, we are going to take minus k, and it is also divided by 1 divided by n naught. This is very simple. So these two are basically that it is telling me about the duality property. So there are some other properties also. There are some other properties. So if xn is real, if xn is real, if xn is real, then c of minus k is equals to c of n naught minus k, and that is equals to ck conjugate. This property is very important. So if xn is real, then c of minus k is equals to c of n naught minus k, and that is equals to ck conjugate. And what is that star? So star denotes the complex conjugate. This star denotes the complex conjugate. Now we have even and odd sequences, even and odd sequences. So if xn is real, then we have xn that is equals to even, it can be represented, xn can be represented of the sum of even and odd part. So it is xen plus xon. What is xen? Xen is basically the even part of xn, and what is xon? Xon is basically the odd component of xn. So if xn has discrete Fourier series that is equals to ck, then xcn, if we find out the discrete Fourier series of xcn, that is equals to real part of ck, and if we find out the discrete Fourier series of xon, that is j times imaginary part of c of k. So thus we can see that xn is real, then its Fourier coefficients are real, then its Fourier coefficients are real, while if xn is real and odd, its Fourier coefficients are imaginary. Next very important property is called the Parseval's theorem. Parseval's theorem. So if xn is represented by a discrete, Fourier series, so if xn is represented by discrete Fourier series, then it can be shown that 1 divided by n naught summation n over the range of n naught modulus of xn whole square, that is equals to k over the range of n naught modulus of ck whole square. This relation is called the Parseval's identity. So this relation is called the Parseval's identity, or it is also called the Parseval's theorem. It is also called the Parseval's theorem for discrete Fourier series. Now let us see a very important, that is called the discrete Fourier transform. That is discrete Fourier transform. So what is the discrete Fourier transform? So let xn be a non-periodic sequence, of finite duration, that is for some positive integer, n1, xn is equals to 0 when we have modulus of n greater than n1. So such a sequence is basically this sequence is basically what we can say, it is non-periodic, but it is limited to some value. Like if we have this type of sequence, so it is minus n1, it is plus n1, and this is xn. So basically this is non-periodic, but it is limited from minus n1 to plus n1. So let x n naught n be a periodic sequence, let n naught n be a periodic sequence formed by repeating this xn. Basically we are going to repeat this xn, formed by formed by repeating xn with fundamental period n naught n naught. So let us take one signal xn naught n. So xn naught n is basically we are going to repeat it. We are going to repeat it. So this is minus n1 to plus n1. Then again we have n naught. Here we have minus n naught. So this is x n naught n. So basically we have repeated. So this one is basically, this one is xn. Again this is repeated. Again here this is repeated. So basically if n naught is infinity, I am saying that if n naught tends to infinity, if the fundamental period tends to infinity, then what will happen? Then if we apply the limit n naught tends to infinity, then this x n naught n, if this n naught is infinity, then only this xn will be there, because we don't know where is infinity. So this limit n naught tends to infinity, n naught n is basically only this xn, is basically xn only if n naught tends to infinity. So this discrete Fourier series, so what I am saying, that limit n naught tends to infinity x n naught into n is equals to xn only. So the discrete Fourier series, Fourier series of x n naught n is given by x n naught n, that is equals to summation k is equals to n naught ck e raised to the power jk ohm naught into n. And what is ohm naught? Ohm naught is equals to 2 pi divided by n naught, where ck is equals to 1 divided by n naught summation of n over the range of n, capital N naught x n naught n e raised to the power minus jk ohm naught into n. So basically what times I want to tell you that we have taken a non-periodic sequence xn and a periodic sequence x n naught n. Now if n naught tends to infinity, this xn is equals to this expression. So we can further represent it in the form of Fourier series. So we have just represented it in this form of Fourier series, okay, because it is a periodic sequence, of course. So since x n naught n is equals to xn for modulus of n less than or equal to n1, okay, and also since xn is equals to 0 outside the interval, so what is going to happen, that ck can be written as 1 divided by n naught because this n naught x n naught n is equals to x n, and it is only from minus n1 to plus n1. So it is n is equals to minus n1 to n is equals to plus n1 xn e raised to the power minus jk ohm naught into n. So this ck is equals to 1 divided by n naught summation n is equals to minus n1 to n is equals to plus n1 xn e raised to the power minus jk ohm naught into n, and that is equals to 1 divided by n naught summation n is equals to minus infinity to n is equals to plus infinity xn e raised to the power minus jk ohm naught into n. So let us define x ohm as x ohm is equals to summation n is equals to minus infinity to n is equals to plus infinity xn e raised to the power minus j ohm n. So that Fourier coefficient ck can be expressed as 1 divided by n naught into x k ohm naught. Now what is happening here, if we find out x n naught n by using this expression, what we will get? We will get summation k is equals to n naught range, that k will vary over the range of n naught, 1 divided by n naught x k ohm naught e raised to the power j ohm naught into n. Finally, what we are getting? We are getting x n naught n is equals to 1 divided by 2 pi summation this k over the range of n naught x k ohm naught e raised to the power j k ohm naught n into ohm naught. So what we are going to get finally is that basically this x ohm is periodic with period 2 pi. So basically this x ohm is periodic with period 2 pi. This x ohm is periodic with period 2 pi. So also e raised to the power j ohm naught n is also periodic with period 2 pi. So what we are getting, that the product x ohm e raised to the power j ohm n. So what we are getting here, that the product x ohm e raised to the power j ohm naught n will also be periodic with period 2 pi. So it is also periodic with period 2 pi. It is also periodic with period 2 pi. Now if we just draw the diagram, please understand this diagram. So if we have a diagram like this, let us draw this diagram in next slide. So if we have this diagram, so if this y-axis is x ohm e raised to the power j ohm n, and here we have ohm. So if we take a small area, if we take a small strip, this rectangular strip, and that width is ohm naught, and this is k ohm naught, this is 0, this is pi. Again this at this peak it is 2 pi because it is repeating. Here we have minus pi, here we have minus 2 pi because this is repeating after 2 pi. So what we are getting here, that this height is x ohm naught e raised to the power j k ohm naught into n. So what we can see from this figure, each term in the summation represent the area of rectangle of height x k ohm naught e raised to the power j k ohm naught n, and what is the width is ohm naught. So this is a basically that is small strip, that is small area. Okay, so as n naught tends to infinity, so what we are getting that as n naught tends to infinity, as n naught tends to infinity, this ohm naught is equals to 2 pi divided by n naught tends to 0. So it will become this ohm naught will become very small, that is infinite small, infinite t small. So because ohm naught tends to 0 when we have n naught tends to infinity. So this basically what we are getting that since the summation in that equation that we have written of xn, in the xn equation, the summation over the n naught consecutive intervals of width ohm naught, that is equals to 2 pi divided by n naught, the total integration will always be a width of 2 pi. Please understand that the total integration will always width of 2 pi. So when we have n naught tends to infinity, this xn is nothing but it is equals to 1 divided by 2 pi. We are just going to integrate this. We are going to integrate x ohm e raised to the power j ohm n over that 2 pi interval. Okay, over that interval of 2 pi. If we so we will get the value of xn. If we integrate this x ohm e raised to the power j ohm naught n over that 2 pi, then we will get xn. So what we are getting here that there is a Fourier transform pair. What is that? There is a Fourier transform pair. Please understand that there is a Fourier transform pair. So x ohm is basically the Fourier transform of xn, and that is also this is not a simply Fourier transform, this is basically the discrete time Fourier transform. This is discrete time Fourier, this is discrete time Fourier transform. So x ohm is the Fourier transform of xn, that is equals to summation n is equals to minus infinity to plus infinity xn e raised to the power minus j ohm n. So if we find out xn, that is Fourier inverse of, that is Fourier transform inverse of x ohm, that is Fourier transform inverse of x ohm, and that is equals to 1 divided by 2 pi integration over 2 pi x ohm e raised to the power j ohm n into d ohm. So we have a Fourier transform pair, that is x ohm n is Fourier transform. This is Fourier transform pair. This is Fourier transform pair. Let us see the Fourier spectra. Let us see the Fourier spectra. Fourier spectra. So the Fourier transform x ohm of xn in general complex, it is in general complex, can be expressed as x ohm is equals to modulus of x ohm e raised to the power j 5 ohm. So what is happening here, that as in case of continuous time, the Fourier transform x ohm of a non-periodic sequence xn is a the frequency domain specification of xn and is referred to as the spectrum of Fourier transform of xn. Okay, so we have two types of spectrum. One is called that magnitude spectrum. So this is called the magnitude spectrum. Magnitude spectrum of x ohm, and also we have phi ohm, that is called the phase spectrum of x ohm. So we have two types of spectrum. One is called the magnitude spectrum, another one is called the phase spectrum. There is another thing that we need to understand, that is called the convergence of x ohm. That is convergence of x ohm. So what is that? Just in case of continuous time case, the sufficient condition for the convergence of x ohm is that should be absolutely summable. So what does that mean? That if we just take summation of from n is equals to minus infinity to n is equals to minus infinity to n is equals to plus infinity modulus of xn, that should be less than infinity. So it should be absolutely summable. This is the convergence condition for x ohm. This is called the convergence condition of x ohm. So let us discuss one basically the connection between the Fourier transform and Z transform. Let us see the connection between the Fourier transform and the Z transform. So we have x ohm, that is equals to summation n is equals to minus infinity to plus infinity xn e raised to the power minus j ohm n. Now the Z transform is equals to xz summation n is equals to minus infinity to plus infinity xn z raised to the power minus n. So this x ohm is related with the Z transform xz when we have z is equals to e raised to the power j ohm. When we have z is equals to e raised to the power j ohm. If we put z is equals to e raised to the power j ohm, that is equals to x ohm. So what is happening here that since the summation in this equation, this Z transform equation, let this is equation number 1, this is equation number 2. So since the summation in the equation number 2 is denoted by xz, then the summation in equation number 1 must be denoted by x is raised to the power j omega. So obviously if x ohm, or we can write it as x e raised to the power j ohm, that is same thing. Same thing. So somewhere we can find out this notation and somewhere we can find out this notation. So it should be basically that is the basically x ohm and x e raised to the power j ohm we can change interchangeably. We can use interchangeably. So because of the Fourier transform of Z transform is Z. Basically that Z is equals to e raised to the power j omega. If we replace Z with e raised to the power j omega, that is equals to x ohm. That is the discrete time Fourier transform. So if xn, that condition is if xn is absolutely summable, if xn is absolutely summable, what we will get that if xn is absolutely summable, that is xn satisfied that condition that I have written summation n is equal to minus infinity to plus infinity, it should be less than infinity modulus of xn. So the Fourier transform of xn can be obtained. So if it is absolutely summable, the Fourier transform of xn can be obtained from the z transform of xn, from the z transform of xn with replacement of z with e raised to the power j ohm. Since the ROC of xz will include the unit circle, it means the ROC of xz should include the unit circle, because so the ROC of xz should include the unit circle. That is not generally true of sequences which are not absolutely summable. So basically, if we have sequences which are not absolutely summable, so this Fourier transform from Z transform is not possible. The Fourier transform from Z transform is not possible. If the sequences are not absolutely summable, then Fourier transform of from Z transform is not possible. Consider that example, consider a problem. So if we have a unit sample sequence, if xn is a unit sample sequence, then let us find out the Fourier transform of that. So Fourier transform of del n is equal to summation n is equal to minus infinity to plus infinity del n e raised to the power minus j ohm n. Now applying the sampling property, what we will get, we can write it as n is equal to minus infinity to plus infinity del n only, because this n is equal to 0 will produce it this term to 1. Now it is simply we can say that it is 1. So what we can find out that also the z transform of del n is equal to 1. So what we can find out that thus the z transform and Fourier transform of del n are same, because it is a simply summable sequence, because del n is simply because del n is summable. If we find out the summation n is equal to minus infinity to plus infinity del n, that is equal to 1, that is less than infinity. Because del n is absolutely summable, not only summable, it is absolutely summable. It is absolutely summable. Let us consider another problem. So consider a causal sequence xn that is equal to a raised to the power n into un, where a is a real quantity. So let us find out the Fourier transform. So before finding out the Fourier transform, let us discuss the Z transform. And after finding out the Z transform, if the sequence is absolutely summable, then of course that Fourier transform is also possible. So let us find out the Z transform. So the Z transform of this is equals to 1 divided by 1 minus A Z inverse. And the ROC is modulus of Z greater than A because it is a causal sequence. So when in which condition that x e raised to the power j ohm exists means we need to find out the condition. We need to find out the condition. On that condition, the Fourier transform will exist. So we can find out. We can see that thus x e raised to the power j ohm exists for modulus of a less than 1. So if we have modulus of a less than 1, then x e raised to the power j ohm that Fourier transform will exist because the ROC of xz, the ROC of xz because the ROC of xz then contains the unit circle. Let us see that xz is equals to 1 divided by 1 minus az inverse, and this is modulus of z greater than modulus of a. Now if we have case that if a is less than 1, another case is if a is greater than 1. So suppose this is a unit circle. This is a unit circle. Now a less than 1 means this is inside that circle and this is the ROC. This is the ROC. Because exterior to that. So this is A. So modulus of Z greater than modulus of A. That is the ROC. Now another case is if that unit circle, if we have this unit circle and a greater than 1, that is here we have a that is greater than 1. So if it is unit circle, it is a, then the ROC is like this. This is the ROC. That is ROC, that is modulus of Z greater than modulus of A. So what is that? This ROC will not include the unit circle, not include unit circle. Here the ROC is including the unit circle. ROC is including the unit circle. So here the ROC is including the unit circle, here ROC is not including the unit circle. It means that for a greater than 1, this ROC is not including the unit circle, and for a less than 1, the ROC is including the unit circle. So for a less than 1, that discrete time Fourier transform is possible from Z transform. This discrete time Fourier transform is possible from Z transform. So what is that DTFT? So for modulus of a less than 1, this x e raised to the power j ohm, we can find out that it is equals to 1 divided by 1 minus a e raised to the power minus j ohm, and it is only for modulus of a less than 1. Also by the definition we can find out that we can find out this expression by definition. It is summation n is equals to minus infinity to plus infinity a raised to the power n un e raised to the power minus j ohm, and that is equals to summation n is equals to 0 to infinity a n e raised to the power minus j ohm n, and that is equals to summation n is equals to 0 to infinity a e raised to the power minus j ohm raised to the power n, that is equals to 1 minus a raised to the power minus j ohm. 1 minus a raised to the power minus j ohm, and we have a raised to the power minus j ohm should be less than 1. That is modulus of a less than should be less than 1 for convergence of this series. For convergence of this series, this term, we can see that modulus of a raised to the power minus j ohm should be less than 1. Otherwise, the series will not converge. So, x ohm is equal to xz when we have z is equal to e raised to the power j ohm. Because for that condition modulus of a less than 1, this xn will be absolutely summable. So xn will be absolutely summable. Xn will be absolutely summable when modulus of a less than 1. So when we have modulus of a less than 1, this xn will be absolutely summable. Let us see another example. So consider the unit step sequence un. Now z transform of un is equal to 1 divided by 1 minus z inverse and modulus of z greater than 1. So the Fourier transform of un, basically the Fourier transform of un cannot be obtained from z transform, because if we just see that minus infinity to plus infinity un, that is not summable. That is not summable. Okay, it means that the unit circle is not included. It means the z transform. It means the z transform does not include the unit circle. We can see from that expression we have modulus of z greater than 1. This is the ROC. So this is the unit circle. So that ROC does not include the unit circle. That's why this z transform directly, that Fourier transform from z transform directly is not possible. So basically we will see later that the Fourier transform, if we find out the Fourier transform of un, then we need to from z transform it is not possible, but we can find out the Fourier transform of un, and that is equal to pi del ohm. Later we will prove that, plus 1 divided by 1 minus e raised to the power minus j ohm, and we have modulus of ohm less than or equal to pi. We have modulus of ohm less than or equal to pi.